Okay. So welcome to the model checking session of VMCAI'. So we're going to have 3 talks here. 2 of them will be virtual and 1 will be in person. So the first talk is Automata-Driven Partial Order Reduction and Guided Search for LTL Model Checking. I'll be presented by Nikolaj, Jensen, Ulrik. Go ahead.
Yes. Yeah, so my name is Nikolaj, and I will be presenting a paper, Automata-Driven Partial Order Reduction and Guided Search for LTL Model Checking. The problem we are trying to address with this paper is that of LTL model checking, which briefly summarized is given some kind of a system, given a state graph and a formula K, or a formula phi, sorry, we want to determine whether K satisfies the formula. The sort of standard classical approach is that we construct a non-deterministic Buchi automaton equivalent to the negation of the formula, and then try to find accepting cycles in the products of our state space and the Buchi automaton. Some issues are that, well, the state graph can be exponentially or even infinitely large due to combinatorial state space explosion. And the other issue we'd like to look at is, well, to determine the answer to a formula, we need to find just one counterexample to prove it false. So can we be smart about how we search for it? Our proposed solution for both of these issues will be to exploit information about the current state we're in the Buchi automaton, wherever we are in this product here. So we'll be doing an automaton-driven approach to address these issues. More concretely, we'll be developing an automaton-driven heuristic for guiding the search towards counterexamples more quickly. We'll be showing an automaton-driven partial order reduction technique that uses stop-on sets to combat the state space explosion problem. We'll be applying both of these methods to the theory of Petri nets, and we'll be implementing this in the model checker TAPAAL and comparing performance experimentally. So on the left, we have a Buchi automaton with 3 states, Q0, Q1, and QAccept. Our view of the automaton will be strictly local. So in other words, when we're in Q0, for example, we look at just the transitions that go out from this particular state. Here we have 2 transitions that go outward with labels A and B and labels A and not B. Collectively, we call these the progression formulas of Q0. Q1 has a formula that would go to the state itself. We refer to this as the retarding formula, which in this case is not A. Finally, in some cases, there will be formulas that do not provide us any good successor. If in Q0, for example, A does not hold, there's no successor, which we can implicitly model using a non-accepting sync state here, and refer to the sync state formula as not A in this case. So there's mostly the guided search, or the algorithms we use to detect the counterexamples in the formula are depth first ordered, which means that the choice of successor is the performance is very sensitive to which successors do we choose in any given state. For example, if we here go to do the action beta, we would end up in a nice region of the state space where there is a counterexample here, SQ0, looping in S prime QAccept. But if we choose poorly instead and go do the action alpha, we land in a potentially very large region of the state space that we have to explore exhaustively before we can backtrack. Even worse, in our case, we're interested in working with Petri nets, and in that case, the state space can be infinitely large. So we will never find a counterexample, even though there was one right under our noses over in the right-hand side here. The heuristic we will attempt to address this with is based on the fact that to generate a counterexample, we must get to an accepting state, Q1 or Q3 in this case here. In Q0, this means that we have to satisfy the formulas B1 or B2 somehow. In other words, we can sort of reformulate this as the reachability problem, satisfy B1 or B2, which we'll apply in just a moment. What we do then is, given some successor states, we compute a heuristic estimate for example, h of b1 and h of b2, where h is some heuristic estimate. We compute this and take for each of the progressing formulas here, b1 and b2, and take the minimum value as the final score for S1. So S1 would have a score of 2 in this case. Doing this for all the states, we get each of the heuristic estimates, but it's 2 in all of these cases. So we didn't gain much in this example. However, we also note that B1 and B2 are not created equally, since satisfying B1 would let us go to Q1, an accepting state, immediately, whereas if you just satisfy B2, we would have to go through another transition before we get to an accepting state. So we scale the heuristic estimates by how far away are we from an accepting state. The estimate for B1 we multiply by a factor of 1, and the heuristic for B2 is multiplied by a factor of 2, which is the distance to an accepting state, 1, plus 1, so we works out nicely. And now we have an unambiguous lowest heuristic estimate over here on S3. So this would be our choice of successor. I want to reiterate this idea that what we did was essentially view B1 and B2 as reachability problems to be solved in this automaton. And the heuristic estimates we use in practice are ones that previously existed in the tool TAPAAL as heuristics helping with reachability analysis. And this will become relevant for the StopSet method. Now, the partial order reduction method we use is using StopSet in particular. The idea is that we want to address the state space explosion problem by reducing the number of interleavings of concurrent actions. Here, for example, is a small fragment of a state space where we have 2 executions, one which goes alpha beta and one which goes beta alpha. And the thought is that, well, there's not much difference between which order we do this in, so maybe we can discard one of these interleavings here, stick to just alpha beta, for example. The StopSet method does this by computing some sort of subset of actions given the current state we're in. Since we are doing it automaton-driven, we'll also consider the Buchi state that we are in. This set is called the StopSet, STFSQ, and any action in this set we'll call a stop-on action. And the reduction then proceeds by just exploring the actions that are in the stop-on set. So in this case, we would have computed a stop-on set consisting of just alpha. I should note that that we're not the first to apply the automaton to these partial order techniques. The first LTL preserving technique was due to Valmari back in 1990, was the progenitor of StopSet techniques, and he provided a nice method that preserves stutter-insensitive LTL. That's what the suffix X is denoting here. One of the big parts of this method was the visibility requirement, which states that in a formula, or rather, the stop-on actions should not change whether atomic propositions in the formula are satisfied or not. In 2001, Pellet, Valmari, and Kokerinen relaxed this method or this requirement by taking into account the automaton, specifically saying that we only need visibility with respect to the reachable parts of the Buchi automaton. In 2011, Lehman et al. Developed a specialized StopSet technique that considers just very weak formulas, which are named so because of a structural property in the Buchi automaton. And in 2020, Liebke generalized some of these ideas into an automaton-based method that works for arbitrary LTL formulas, but without giving any kind of implementation. Our work is also an automaton-based StopSet method, which we do implement and also show experimentally to perform better than Liebke's method. So our method is based on reusing this concept we had before in the guided search, where we look at the progression formulas and treat them as reachability problems, and then add additional rules to ensure we preserve LTL. The StopSet method stipulates that when we generate a StopSet, it should satisfy these 4 rules. The first rule, the COM rule, says that for any alpha which is stop-on and W which is a string of non-stop-on actions, if we can fire W then alpha, then we can also fire alpha then W. This is the classic standard stop and set rule. And this is one also that captures this phenomenon of reducing interleavings of actions. The rule R says that if we fire a sequence of non-stubborn actions from a state which does not satisfy formula B, then the resulting state S prime also does not satisfy formula B. The converse of this is that if we do land in a state that satisfies B, then there must have been a stubborn action in the sequence W. And together, classic result is that with common R, we satisfy or we preserve reachability of state satisfying formula B. We then add onto this the key and safe rules. Key requires that if Q here is an accepting state and S is not a deadlock, then the stubborn set must contain an enabled action. This is in order to ensure that we do not accidentally introduce accepting runs when we are in an accepting state. And then lastly, the safe rule, which I'll elaborate on in just a second, says that enabled stubborn actions should not cause the Buchi state to change. And our theorem is, or the theorem that we show is that if we satisfy the rules com, R, key, and safe, then the reduced state space preserves LTL. In other words, the full state space will contain an accepting run if and only if the reduced state space does. I just briefly quickly explain why we care this safe rule is there, because it's a pretty costly one, but it's also very important. Here we have, on left, we have a state space with two executions, one that goes beta, gamma, alpha, and one that goes alpha, beta, gamma. And on the right, we have a Buchi automaton with a property we want to verify. If we walk through the executions, we'll see that there's a problem if we try to reduce here. Following the upper path of the state space, we go to S1. There's no A here, so we stay in Q0 in the Buchi automaton. Afterwards, we stay here. Afterwards, we go to S2. We still stay in Q0, and then we go do our alpha action and then go to S2 prime. In this case, there is an A in the state label, so we go to the accepting state. And there's a looping transition here and an A in the label, but no B. So we loop here, meaning that this is an accepting path and thus a counterexample to the formula here. However, if we do alpha first, which might be the case if we're applying a stubborn set reduction, we might discard the upper path. Then we land in S0 prime here, where A is satisfied immediately. We go to Q accept, but now once you do the beta action, notice that there's a B in the label here in S1 prime, which means that we land in the sync state, and thus there will be no accepting run following this path. So in fact, we have to be very careful about, can we reduce in this S0 state? And the answer is that we would not want to reduce, as we are about to change state over here. So we'll end up in Q sync here. So the way we capture this issue is by the notion of a safe action, which is an action that's, we say that action alpha is safe with respect to phi if alpha does not make phi more true. More formally, this is specified as in state S for any W such that as firing it lands in a state where phi is not satisfied, then prefixing alpha to W will still not lead to a state satisfying phi. And the way we apply this is that we require that all enabled actions in our stubborn set must be safe with respect to the progression formulas as well as the sync state formula of the Buchi automaton. And S must not, or state must not satisfy any of these formulas either. This is saying that all stubborn actions do not make the progression formulas more true, and the progression formula is not true right now. Time briefly. I'd like to finally walk through an example of how we apply this method to a Petri net, also more generally. So the Petri nets consists of places marked with circles and transitions marked with squares, and the arrows indicate whether the dependencies of a transition. T1 here is enabled, since there's an arrow pointing from a place with a token but since this error here comes from a place with a token in it. The first thing we do in the method is to apply the safe rule, checking that we are not about to change Buchi state. So P4 greater than 1 should not be satisfied, which is not in this case. We then apply the OR rule, which consists of computing the transitions that could cause P4 to become satisfied. This is denoted by this AM here of P4 greater than 1, which will compute the set T3. We then apply the COM rule to this set, trying to, or where we find all transitions that would not interleave with T3. First, we see that, okay, the transition T1 would produce a token in a place that is a dependency of T3. So we should add T1 to the stubborn set. T1 shares a dependency with P1, or shares a dependency with T2, namely P1. So we add T2 to the stubborn set, and that's the application of the COM rule. We check whether we need to apply the key rule. In Q1, we don't need to do this. If we were in an accepting state, we would ensure that we have some enabled transition in our stubborn set. And finally, we check the safe requirements, which, remember, says that enabled stubborn actions should not be unsafe. The safe actions are exactly the interesting transitions, same as before, and the enabled action here are T1, T2, and T4. Since there's no overlap between the enabled stubborn actions, which are just T1 and T2, and the unsafe actions, T3, we're good to apply the reduction here. And notice how the final set here does not contain the enabled transition T4, so we do actually reduce the state space in this case. We implemented these methods and evaluated them experimentally. So we implemented the stubborn sets and the heuristic as extensions of TAPAAL, and it's available in TAPAAL 3.9. You can download from tapaal.net. We also implemented the classic method by Valmary, and the automaton technique by Liebke for the sake of comparison. The benchmark is that of the model checking contest 2021, which contains about just under 1,200 Petrinets and 32 formulas per Petrinet, giving us almost 38,000 problem instances. And we filtered to sort of a medium difficult set of non-trivial but solvable instances. And we run each configuration for 15 minutes per formula with 16 gigabytes of RAM. We present the results here as in the form of cactus plots, where for each configuration, we log the time it takes to solve each formula, and then sort these solution times independently for each configuration. So there's no way to compare the methods on the x-axis, but you get these large-scale performance trends. What we can see of it is that on the left here, where in the blue line, we have the baseline configuration. And the yellow line here, just next to it, is the Valmary method, the classic partial order method. And it improves by a decent margin over the baseline. Liebke's partial order method improves slightly over the classic method, but our method on the far right here improves significantly over both Liebke's and the classical partial order reduction methods. By a pretty wide margin, you can see also about as much gain compared to Liebke's method as compared to the baseline method. These were all without applying the heuristic for guided search. Applying the heuristic gives a massive gap here. You see that you gain much more by applying the heuristic than by applying the partial order method. But luckily, these gains are also additive. So you see that the classic using Valmary's method with the heuristic still improves over using not Valmary's method. Liebke's method improves again a bit, although we note that on the harder problem instances up here, there's not much gain by using Liebke's method compared to Valmary's method. However, our method does scale pretty well on harder instances, denoted by a slightly more flat line than the green line here. And finally, we did a comparison to ITS tools who won the second place in the model checking contest, and is in a setup similar to that of the model checking contest, where we have a multi-core setup where we're given an hour to solve 16 formulas using these 4 CPU cores. In the setup, ITS tools solved 87.8% of all queries, whereas TAPAAL solved 94.3% of queries, a 6.5 percentage point increase, which is a very significant margin of about 2,500 actual queries. Compared to without the partial order heuristic, though, there's just 1.1% increase. While this difference may not look like much, it's actually still a pretty significant one, as this benchmark contains a large number of queries that are somewhat trivial to solve. So being able to solve additional, and meanwhile, there's a steep cliff where problems become really, really difficult. So gaining 400 additional answers in this difficult end of the benchmark is actually quite nice. So in conclusion, we developed or showed an automaton-driven partial order reduction technique that improves by a sizable margin over other partial order reduction techniques that we compared to. We saw an automaton-driven heuristic for guiding the search towards counterexamples, which makes a huge difference in the performance on the benchmark. We saw 6.5 percentage points additional answers over the ITS tools in computation, and 1.1% additional answers due to the partial reductions and guided search. That was it for my talk, and thank you.
All right, thank you. All right, let's see if we have any questions. So if you're in a live audience, I guess you know how to ask the question, and if you're online, you can ask it in a question chat.
We have one live question. 1 second.
Thank you. I would like to ask about the benchmarks.
Hold on. Please say who you are, because we can barely see you.
Yes, I'm Jan Onderka here, if you can see me. So I would like to ask about the benchmarks, whether you think that they represent the real world use cases, or whether they are just synthetic. So how much impact would this kind of heuristic have on more real world use cases? If you can comment on that.
Yes, thank you for the question. So about the benchmark quality, these queries are randomly generated. So, and now, while there are some queries that do seem meaningful, many of them may not make so much sense. So it's a bit difficult to estimate exactly how much this gains. But I think that you'll still find that these methods of finding counterexamples will work nicely on real-world examples. Is probably my expectation, but I can't say anything beyond this sort of guesswork.
Okay, thank you. Do we have another live question?
I don't think we have any questions right now.
Okay, let's see. So there is a question from Javier Esparza on the chat. So in partial order, usually there is a condition to guarantee that you cannot keep executing invisible actions forever. Do you also have such a condition?
So let me scroll up to the rules slide. Thank you for the question.
I think you're not... Oh, there's a question on the slides, I see. Like, I don't see your slides, but I see the question.
Can you see the slides in the audience? Okay, thanks. So the way we ensure that we don't execute invisible transitions forever is by having the R rule here. And the way we do this is we ensure that the stop and set contains actions that would lead us closer to satisfying a progression formula. So in other words, the actions that we fire are not will not invariably be invisible. And if there are only invisible actions available ever, then we will simply, then it's fine to reduce. I think the answer. So the short answer is we don't need that kind of rule.
Okay. Is there any other questions, either from the audience or in Q&A? Thomas?
No, I don't think we have any.
Okay, so then I wanted to ask a question since we still have a bit of time. So one question I had is you pointed out that there was a recent method by Lebec or Lipke, and that your method is significantly better. Could you give some intuition what's the difference, since they both, like you say, they both based on automata and exploit maybe similar insights?
Yeah, so the way we describe the difference is that we consider the progressing formulas and the, you find the relevant slide here. So the relevant difference is that we consider the progressing formulas and the sync state formula, whereas Liebke considers the looping formula. I can provide to a nice clean example that demonstrates why this is there's a difference in performance here. All we can see is that when we implement both methods, there's a performance difference.
So do you think it's like one can prove this?
Sorry, can you repeat that?
Do you think it's possible to prove that your method is strictly superior to the previous one?
I'm not sure that would be possible to prove. No, I think they are. They might be disjoint. At least we've not. We've looked into it and not found that this is definitely a strict improvement. Okay. Theoretically, at least.
Okay, and I have another small question about the heuristic search. So you presented the search, and I wasn't clear. Is it similar to A star that's often used in AI?
No, it's not strictly. So our algorithms are very strongly depth-first search algorithms. So this is, you would call this a best depth-first search algorithm. So the way the reachability engine does it in TAPAAL is, I think, not far from A star, where actions are inserted into a priority queue. But this is just, we order successors now, and then we choose one path to follow depth first style. So this is not A star.
I see. And have you looked into like breadth first style searches, like for example, iterative deepening, where you use a depth first, but up to a certain bound?
We have not looked into this, no. Under the hood, we use a version of Tarjan's algorithm, which depends very strongly on having structures that reflect the depth-first stack available to us. So applying these breadth-first searches is not a trivial task to accomplish.
Okay. There's an extra question, right? It's appearing on the screen right now. So it says classical LTL to automata translation produce states annotated with subformulae requiring to halt from the current time. Have you considered exploiting such information?
Thank you for the question. So it's not something we've looked into much. As I understand it, this is what the work of Pellet et al. Was doing, this kind of thing, and there might be potential to this. We've not looked into it.
There's potential for improvement then.
There might be potential.
Well, let's thank our speaker. Thank you.